3B. All right, 11.3b. This is one of my favorite lessons because it involves so much of what you've done over the last couple years in your life, and it brings it all together. It's adorable. Okay, we're going to solve limits today, algebraically. Plus, algebra is probably my favorite subject. It really is. I just love algebra. Like, geometry was never my favorite. Was geometry anybody's favorite? No? Yeah. Okay, so here we go. We've got some techniques to solve limits algebraically. You did one last night where you had to solve it graphically, and it was like, what's the answer? It's kind of hard to tell, so we're going to do them algebraically. Okay, so here are some ways of doing it. Way number one is the dividing out technique. So we're going to get our algebra skills out that we haven't done in a long time, and we're going to remember how to do it. And honestly, in calculus, when people do problems wrong, it's because their algebra is wrong. It's just algebra. Okay, so here we go. We're going to find the limit as x approaches -3 for x squared plus x minus 6 over x plus 3. All right, so let's talk about this. Yes, you can solve this graphically. You can find the answer, but we're not going to do that anymore. We're going to solve this one algebraically. You will not be given a calculator. And so we first start by using direct substitution. If you did direct substitution, you would see that you would get 0 over 0. But that also means that this polynomial has a factor of x plus 3 because we're getting 0 over 0 when we plug in -3. Do you see that? So what we can do is we can factor the numerator. Okay, we haven't factored since, oh gosh, I don't even know when. When was the last time we factored? First day of school? First day of school. All right, so we're going to solve by factoring, we're going to solve the limit by factoring. So up top, you can factor any way that you like. You know, for these, there's the coefficient's 1 in front of x squared, so it's basically what times what's -6 adds up to 1, which would be x plus 3 and x minus 2. Okay, and you know that x plus 3 has to be a factor because when you're plugging in -3, you're getting 0, so it will be. All right, so here's the part where if we were to still plug in -3, we get 0 over 0. Well, let's get rid of that part that's giving us 0 over 0. This part that is x plus 3 and x plus 3, and it's gone now. So now, when you plug -3 in, you can now take the limit. I'm going to rewrite it. You don't have to every time, but I want you to show you what we're doing. So once we've, divided out the x plus 3's, we get this that now we can use direct substitution. And our answer is what? -5. You know, all this graph is it's a line with a hole in it. And the hole is at -3. But just because the hole's at -3 doesn't mean, that your graph doesn't have a value. So it looks like this. Something like that. Okay? And if you go to -3, there's this hole in the graph. And at that hole in the graph, your y value is -5. But that doesn't mean there's no limit. It means that it's approaching -5. Okay? So algebraically, it works out. All right, let's do another one, number 2. Okay, let's do some more factoring. Let's do limit as x goes to 1 for x minus 1 all over x cubed minus x squared plus x minus 1. Ooh. All right. So once again, you try direct substitution because that's the easiest thing to do, and you like to just try that first. And when you do that, you end up with 0 over 0. Okay. So now you have to do some of your algebra techniques. In this case, we're going to take the denominator and we're going to factor this by grouping. It has 4 terms, so we can factor by grouping. Do you remember doing that a little bit? No? Okay. So it has 1, 2, 3, 4 terms, and we're going to factor out what's in common in the first 2. The first 2 have an x squared in common, so we're left with x squared times x minus 1. The second 2 don't have anything in common, so you write a plus 1 because that doesn't change a thing. All right? And then when you factor this, what you're really doing is you have two terms, and they each have an x minus 1 in common. And so you factor out an x minus 1, leaving you with x squared plus 1 left behind. It's been a little while since we've done grouping, right? Okay, so let's rewrite our whole thing here. So we have the limit as x goes to 1. The numerator is x minus 1. The denominator is x minus 1 times x squared plus 1. And that's good news, because you see, when you plug in 1, you're getting 0 over 0 because of these two things right here that can reduce. And so you're left with a 1 up top. And now we can go ahead and evaluate the limit of 1 over x squared plus 1. So take 1 and plug it in, and our answer is, anybody? 1 over 2. Perfect, 1/2. Yeah. Aren't these fun? Don't you love algebra? You really do. Okay, let's do number 3. Now here's the one that you did in your homework. The limit as x goes to 0 of x plus 1 cubed minus 1 over x. And you were told to solve that one graphically. Do you remember doing that at all in your homework last night? The answer was, do you remember the answer? Okay. So you had this one, and you did it graphically, and you graphed it, and you tried to find it. Okay, we're going to do this one algebraically now. All right, so what we're going to do is if you were to plug in 0 once again, you would get 0 over 0. So let's take the top, and we're going to FOIL out x plus 1 cubed. Do you remember how to do that using the binomial expansion theorem? Yeah? Okay. It's funny, when you get to calculus, they expect that you know how to do this stuff. They expect that you know binomial expansion theorem, you know how to factor, you know how to add fractions, you know how to do all this stuff, radicals, like it's crazy. All right, so here we go. We're going to FOIL this whole thing out using the binomial expansion theorem, which is by Pascal's triangle, is 1, 3, 3, 1. Do you remember that? Is that coming back to you? The first term is x cubed, then x squared, and then x. And then this 1 would be 1 cubed, 1 squared, 1. And there's pluses in between all of the terms. And then we still have a minus 1 all over x. Woo! Binomial expansion theorem, Pascal's triangle, 1, 3, 3, 1. I remember having this problem in college, and I didn't use the binomial expansion theorem. I took x plus 1 because I forgot it, and I FOILed it all out, and I got marked off for it. Oh, how dare he? I got the problem right. Okay, the limit, true story. X goes to 0, so let's clean all this up. We've got x cubed plus 3x squared plus 3x, and do you see how this is 1? Minus 1, those will cancel each other out. 1 minus 1 is 0. And this is all over x. Now, I fixed it a little bit, but still, when I plug 0 in, you can see I will get 0 over 0. So let's go ahead, and in the numerator, we're going to factor. We're going to factor out an x from all those terms, so that we're left with x squared plus 3x plus 3 over x. Do you have some algebraic foreshadowing happening, like you know what's going to happen next? The x's are going to reduce, and then you use direct substitution, because we just got rid of, now in my other class I kept calling it the problem area, and people didn't like that. They thought that was gross. So I got rid of the problem area, right? That's what we're all trying to do, get rid of our problem areas. So then you got rid of it, and now plug 0 in, and it's 0 plus 0 plus 3 equals 3. So good, right? Yeah.
Can we just FOIL it out?
Sure, I will not mark you off for that. But you are on a time frame here, time constraint. When you're taking a test or quiz, you want to do the most efficient, quickest way. Because that would be tough to FOIL. Have you ever FOILed that out? You FOIL and then you do super FOIL, and it's like, ugh, and hopefully you get them all right. Okay.
Or you just always going to go to cubed?
Cubed, yeah. I don't give you fourths. Usually in calculus too, it's just cubed. That's as far as they go. Just little. All right, number 2. Second one. So that was our dividing out technique. And now we have what's called a rationalizing technique. Rationalizing kind of, or we could just say conjugates, because I'm going to give you one that actually doesn't have a radical in it, but we're going to use conjugates. So I'd rather just call it conjugates. And I've got 3 of these. Here we go. Number 4. Okay, suppose that we have the limit as x goes to 0 for the square root of x plus 1 minus 1 all over x. All right, and once again, we notice that if you were to plug in 0, you would get 0 over 0, okay? Just notice that, because you want to just plug it in. Direct substitution is the best way to go. But when you can't, you have to do something algebraically. So what we're going to do is we're going to multiply by the conjugate. Do you remember conjugates at all? Yeah? Conjugates differ only by one sign, and that's the sign in the middle. So the conjugate of the square root of x plus 1 minus 1 is the square root of x plus 1 plus 1. Everything else stays exactly the same. And whatever you do to the numerator, you have to do the denominator to keep your fractions equal. All right, so what we're going to do is we're going to take the conjugates and we're going to FOIL them out. Okay? So we get the limit as x goes to 0. Now, conjugates are nice to FOIL, because when you FOIL conjugates, the OI part of the FOIL, those cancel each other out every time. So you don't even have to do them. You just need to do the first. So rad x plus 1 times rad x plus 1. Do you know what that is? Good, x plus 1. My other class, they didn't. No offense, other class. Okay, didn't. All right, and then outside, inside, like I said, are going to reduce or cancel out because it's a positive and a negative, and those make 0. And then I get negative 1 times positive 1 is negative 1. Do not do anything to the bottom. When you do this conjugate technique, you just FOIL the conjugates, and the other parts you leave alone. Okay, you just write them next to each other. Now, you must have some algebraic foreshadowing happening here, do you? No, yeah, you do. Before you even write anything down, look at what you're going to do. Can you see the next few steps happening? Isn't that amazing? Like math goosebumps everywhere. Okay, so you know that 1 minus 1 is 0. So you end up with x, and you have factors of x up and on top and bottom, so you can also reduce those. You saw that. You did. And then you put a 1 up top. And now you take the limit as x goes to 0 of 1 over the square root of x plus 1 plus 1. Do I need to rewrite that, or can you see it? Can you see it? You can rewrite it if you want to. I don't require that step. It's just you get a 1 over rad x plus 1 plus 1. Okay? So now we can finally use direct substitution, because we got rid of, that was the problem, that x over x right there. And you end up with 1/2. Yay! Aren't these so good? Okay, number 5. Let's do. I'm gonna skip one for a minute and go to this one. This one's good. This was from my dad's notes. My dad, he subbed for me one time, and he left me all these notes, and I didn't use them because I thought they were just too much. But I liked one problem. Okay, thanks, Dad. All right, here we go. The limit as x goes to pi. Uh-oh. What do you think we're going to use here? Yes. 1 plus cosine x over sine x. Okay. So, you think, okay, that's not a problem, but once you plug in pi, you get 0 over 0. No good. So what we're going to do is we're going to use conjugates. We're going to multiply top and bottom by 1 minus cosine x. See this? Even in calculus, they think you know how to do trig. They do. They expect it. All right, so here we go. You take the limit as x goes to pi, and we're going to FOIL the numerator. So you FOIL the numerator out, and you get 1 times 1 is 1. OI cancel out. Oi, gone. And then you get cosine x times a negative cosine x gives you negative cosine squared x. And you should be a little alarmed by that. A little excited, maybe. Or, nope, maybe not seeing anything at all. Okay, and then you get sine x times 1 minus cosine x. Some of you see it, though. I know you do, because I see some smiles out there. I see a lot of frowns, too. But there's some smiles out there. And the smilers, they know that 1 minus cosine squared x equals what? Sine squared x, yep. You even smiled when you said it. Sine squared x, using your Pythagorean identities, right? And then you have sine x on the bottom, 1 minus cosine x. So, take a look. We've got 2 signs up top and 1 on the bottom as factors, and we can go ahead and reduce. So that's gone, leaving us with just sine x, and that sine x is gone. So let's talk about this. We're doing the limit as x goes to pi of sine x over 1 minus cosine x. And you're like, well, we didn't really change that much. Yeah, you're kind of right. But now we can evaluate it. Because when you plug in pi, okay, let's go to pi. Here's pi over here. This is the point -1, 0. When you evaluate the sine of pi, what do you get? You get 0. Good. It's the y value. Okay, so you get 0. And when you evaluate the cosine of pi, you get -1. And so we're safe. Because you get 0 over 2, which is 0. So in my other class, they're like, oh, but wait a minute, you don't really care about the bottom. But we do. We need to figure out if the bottom's still 0, because that would be a problem. Okay, what do we got time for? We're going to go on to, should I do one more radical, or you feel okay with the radicals? You feel okay, huh? I knew you were going to say that. Let's go on to fractions, last part. I only have one of these. So this is number 3. So we did dividing out, we did rationalizing or conjugates, and now we're going to do fractions. And this is what, number 5 or 6? 6. All right, last one, number 6. Okay, these are probably the worst for people. So if you've been tuning me out, tune in. Here we go. Limit as x goes to 0, 1 over x minus 8 plus 1 over 8 all over x. Okay. In Algebra 2, you did an entire chapter, it was chapter 9, on adding and subtracting and multiplying and dividing these rational functions. And it's a hard chapter. Every year it's hard. All right, so what we need to do with fractions is we need to combine them together into one fraction up top. So we need a common denominator, okay? So it's the limit as x goes to 0. And so we still are going to have this x on the bottom, but we need to combine these two together. So their common denominator is you're going to need an 8 for both of them, and you're going to need an x minus 8. So you have to get what's common to both of them. That's why it's called a common denominator. Do you remember doing this at all? It's been a long time. Yeah. Okay. So let's take a look. We're trying to get this fraction equal to this one now. So as you can see, I have the x minus 8. I don't have the 8. So I need to multiply this fraction, top and bottom, by 8. And that will give me the right thing here. Okay? Over here, we have 1 over 8. And so I'm missing the x minus 8. So I'm going to multiply this fraction, top and bottom, by x minus 8. Is everyone okay with that? We've got a common denominator. We're going to add our fractions. So now let's go ahead and combine the fraction in the numerator of the big, huge fraction, okay? So we have 8 plus x minus 8. What does that leave us with? Just x, yeah, because there's an 8 and a negative 8. That leaves us with x over 8 times x minus 8. All of this is still being divided by x. Okay, take that x and turn it into an x over 1. Now you have a fraction. You see what we're going to do? Over a fraction. You're going to take this and you're going to do what with it? Yes, multiply by reciprocal, flip it and write it right here. So now it's gone from there, and we've taken it from underneath and multiplied it by the reciprocal. And look what happens. you see what's happening? 0 is going in, I'm getting 0 over 0. But once I reduce that, it's gone. We got rid of it. So now I take the limit as x goes to 0 of 1 over 8 times x minus 8. So I've got rid of the part where it's giving me 0 over 0. Now I can finally use direct substitution, and I get 1 over what? Negative 64. How would you like to find that on a calculator? I wouldn't. I don't think you'd be able to.
What happens to that?
Yeah, so x becomes 0. So you use direct substitution. You take the limit, and you get the answer.